Hello, Chem 2, and welcome to the second half of the unit on all the review stuff from Chem 1. This chapter happens to talk about atoms, molecules, and ions, and we're going to focus a lot more on naming, structure of atoms, and the like. So let's get started. So this particular chapter has the following objectives. We're going to talk about what a nuclear symbol is, how to relate atomic mass, atomic abundance, or isotopic abundance, average mass, and then be able to relate atomic mass to Avogadro's number, which you may have been introduced to in Chem 1. Relate elements to the periodic table. We're going to be able to read the periodic table much more effectively as a result of Chapter 2. Relate structural, condensed, and molecular formulas. Talk about charges of ions, and then be able to write formulas from their charge of their ions. So all that's going to happen as a part of Chapter 2, but we're going to focus a lot more on the first two, the nuclear symbol and the atomic mass. And we're going to get a little bit into how to use Avogadro's number in this particular PowerPoint. In Chapter 2, we are going to skip the first two sections. I don't think it's necessary at this point after what you did in Chem 1 to rehash Rutherford's intentions and what Thomson had to do with it, nor do I have to really go dig in deep over the structure of the components of an atom, the proton, neutron, electron. I think you got that by now. But we are going to talk about some of the quantitative properties, being able to determine how many of each one of those parts are and how to get that information out of the periodic table. So let's get started. So section 2.3 is all about quantitative properties. And it's going to start by talking about the atomic number. And in chemistry, sometimes we use the symbol Z. Not very often, but when it's in a bigger equation, they'll use a symbol Z to identify the number of protons. The whole number on the periodic table represents the atomic number. So the atomic number, or the periodic table, is listed according to the atomic numbers, like hydrogen being 1, helium being 2, lithium being 3, and so on and so forth. That number represents the number of protons that are in the nucleus of that atom. Another number that is a whole number is what's called the mass number. And very often that gets confused with the concept of atomic mass, and we'll deal with that in a little bit. The mass number is the total number of things in the nucleus. The word that gets used there sometimes is nucleons. The number of nucleons in the nucleus. So it'd be the sum of the protons and the neutrons together that are in the nucleus. There are different sizes of atoms. They're called isotopes. So you might have, for instance, they list here two of the naturally occurring isotopes of uranium, uranium-235 and uranium-238. Uranium-235 has 35 and a mass number of 235. Uranium-238 has a mass number of 238. That means even though both of them are uranium has an atomic number of 92, so it has 92 protons. The two different versions of the atom have a different number of neutrons. Uranium-235 has 143 neutrons, and uranium-238 has 146. So sometimes we'll write it like this down at the bottom, where we'll talk about what's called the nuclear symbol. And then the nuclear symbol, what's going to happen is the top will become the mass number. And if the bottom number is written, that's going to be your atomic number. Now, very often that bottom number is not written because it's kind of redundant if you have a periodic table to say U with a 92, because uranium is element number 92 on the periodic table. So a question, just to see whether you kind of get this. You have an isotope of antimony that has a mass number of 51. It's used to detect tracers of leaks in oil pipes. It's a way to be able to detect whether something's coming out. And this isotope has 73 neutrons in the nucleus. So it has an atomic number of 51, but it has 73 neutrons. So what's the nuclear symbol? So that's kind of easy. If Z is 51 because it's antimony, and it has 73 neutrons, it wants to know the nuclear symbol. So what we're going to do is Z, we know, is the atomic number. That's the number of protons there are. And since that bottom number is the number of protons, we're going to put where that Z is, that 51. And the top number, we need to figure out what the mass number is, and the mass number is the total of protons plus neutrons. So we need to add those together. So the symbol we get is SB as being the symbol. That's for antimony. 51 goes down to the bottom, and 124 goes on top. This would be referred to as the nuclear symbol. Again, very often this 51 is eliminated. It's kind of, like I said, it's kind of redundant. Okay, next idea, next concept, quantitative concept, is atomic masses. And this is the part where I was telling you now we're going to deal with those decimal numbers. On a periodic table, there's a whole number and then there's a decimal number in each cell. That decimal number is the atomic mass. It will tell you how heavy the average element is, the average version of that element. So, for instance, if you look on a periodic table, carbon has an atomic mass of 12.0107 or somewhere near there, depending on the periodic table you have. That means, on average, the mass of a carbon atom is a little over 12. Well, there are different isotopes of carbon. There's carbon 12 naturally occurring, carbon 13 naturally occurring, and to a very, very small degree, carbon 14. Carbon 12, by definition, has a mass of 12, exactly 12, and the unit they use as that reference is atomic mass units. Carbon 13 has a number that's very, very close to, but not exactly 13. So, knowing that carbon 12 has a mass of, knowing that carbon 12 has a mass of exactly 12, but we know the average mass of carbon is a little over 12, that means there's some small amount, very small amount, of the other isotopes. How do we do the math for that? Well, we use what are called isotopic abundances. Basically, it's percentages. It tells you what percentage of each isotope are present in nature, which uses what's called a mass spectrometer. When I was in industry, that was one of the pieces of equipment that I had an opportunity to use, a mass spectrometer. What it does is it will gasify, heat up the material at a very, very high temperature, and then send it through a magnet, through a magnetic field. Well, the heavier objects, because they are heavier, will more easily go straight through, and the lighter ones will turn a little bit in the magnetic field. Well, if the ones turn a little bit in the magnetic field, a different amount than the ones that go straight, you can figure out how much they've been deflected, and based on how often that section of the detector is hit, you can tell the relative abundances or quantities or percentages of the different isotopes that are present. So here's a picture of a mass spectrometer. You have the gas insert. You have it going through this magnetic field here, and then it turns. It turns a different amount, and some turn and hit the detector. Some might turn over here, and you gauge how much of the material hits the different sections of the detector. This one happens to change the magnetic field a little bit for the different numbers. So how do we use that? Well, if we know, using a mass spectrometer, the mass of fluorine is found to be approximately 1.583 times as heavy as a carbon 12. Therefore, we know that an average mass of fluorine is 19 AMUs. We look at relative to carbon as being the indicator for the amounts. Well, now we have to worry about the abundances. We're going to use the amount of the percent, the isotopic abundances, to figure out the average mass of each one of the atoms. So this is a graph that you might get off of a mass spectrometer. You'll notice it has two peaks. What that's telling me is I take the sample is chlorine. I take this chlorine atom, this mixture of chlorine, naturally found mixture of chlorine, and I shoot it through the mass spectrometer, and I get two peaks. Not 3, not 4, not 1, I get 2. That tells me there are two different masses, two different sizes, two different isotopes of chlorine. One is at a mass of very close to 35, one is at a mass of very close to 37. That means I have chlorine 35 and chlorine 37 in my sample. Now look at these heights, these peaks. This is showing you basically if you pile them up like marbles, the higher the peak means the more there are. There's a very large, much larger percentage of material that is chlorine 35 compared to chlorine 37. Matter of fact, I look at this, it's somewhere really close to 75-25. We'll see on the next slide exactly how much it is. But it's very close to 75-25. So 3/4 of all the chlorine atoms in nature are determined to be chlorine 35, and about 25% are chlorine 37. So if I want to figure out the average, I want to figure out the average mass of the average element, we're going to do a weighted average. Now, you already understand what a weighted average is because your grade in all of your classes are weighted averages between the um, formative and the summative points. Our class happens to be a 70-30 class. 70% of your grade will come from your summative points, and 30% of your grade will come from the formative points. Same thing here, but where those percentages come is what percentage from the mass spectrometer, what abundance was each one of them. Well, a chlorine 35 has an actual mass of 34.97 AMU, and there are in the sample we saw there 75.53% of the sample is of the first isotope. The second one is the second mass is 36.97 AMU, very close to 37, times the 24.47, which is the remainder AMU. You do that math where you do each part separately, mass times percent plus mass times percent. Each of the percents divided by 100. So literally you're taking a decimal of the percent. 75% would be 0.75. And when you add those two numbers together, you get a number that's in between. In this case, I get 35.46. Now let's think about that. I get 35 and a half. It goes from 35 to 37. It's much closer to 35. That makes sense because there's more of the 75. Let's use the example of your grade. Okay, suppose on all of your homeworks you get a grade of 100%. On all of your tests, you get a grade of 80%. Okay, just going to use an example. Not saying that's the case. Well, when you average that out between 100 and 80, you're not going to get a percentage of 90 because the weight of the tests is greater. So your grade is actually going to be closer to the 80%. So it's going to be somewhere around 83, 84%. Okay. One of the reasons why you want to make sure you study and prepare very, very well for your tests. Okay, let's move on. Let's take a second example. This one's a little different. This one, we know the masses and we know the average mass, but we don't know the abundances. So we want to figure out what the abundances are of the two. Same idea. We know there's two isotopes, bromine 79 and bromine 81. One has a mass very, very close to 79. One has a mass very, very close to 81. And look at this mass, the average mass. It's really, really close to 80. What that tells me is that the mass, the percentages are going to be really close to 50-50. The fact that my average mass is very close to the middle of my two masses tells me it's going to be very close. Now, I look at this number 79.9, and it's going to probably be a little bit closer to 79 because it's on that side of the 80. But we'll see what it does. So how do we do this? Well, the math concept's the same. We know the mass of each one. We know the average. So now the setup is a little different. The number we don't know is the Y. We don't know the number, the percent of each one of the isotopes. We know the mass. Let me type here. We know the average mass. We know the mass of the first isotope. We know the mass of the second isotope, but we don't know what the Y's are. We don't know what the percentages are. But we do know that there's only two, so the two abundances must add up to be 100%. So we're going to change that a little bit. We're going to change it to be one of them is going to be X. Since it asks for the heavier isotope, we're going to make that X. The other one's going to be 100 minus X. And then you do the math. 79.9, excuse me, 78.92 times 100 minus X over 100. That gives me this. And then 90.2 times X over 100. That gives me this. I do a little algebra, and I get that X, the heavier isotope, is 79%. Sorry, 49%. And like I said, I thought there'd be a little bit more of the lighter isotope. Not much, pretty close to 50-50, but a little bit more of the lighter isotope. So the end point is the atomic mass is about halfway, but just slightly towards the lighter isotope. Okay, last thing, relating atomic masses or masses in general to grams. And in Chem 1, towards the end, when you were doing stoichiometry, you were introduced to Avogadro's number, 6.02 times 10 to the 23rd, and you were given some ratio there. Well, what that represents is the number of atoms in an atomic mass of an element. That's the number of atoms that are in one atomic mass. So, for instance, if I had 1.008 grams of hydrogen, I would have 6.022 times 10 to the 23rd grams of hydrogen. Atoms of hydrogen. If I had 4.03 grams of helium, I would have 6.022 times 10 to the 23rd atoms of helium. That number off the periodic table represents the mass of exactly one Avogadro's number of the atoms. So let's look at arsenic. Arsenic is a classic poison used in crime stories. You hear it all the time. And Avogadro's number is 6.022 times 10 to the 23rd. Determine the mass of a single one arsenic atom. So we know we're looking for the mass of one atom. We know that there are 6.022 times 10 to the 23rd atoms in an atomic mass. So if I know I'm looking for one atom, there are 6.022 times 10 to the 23rd atoms in a mole. Okay. Got a little ahead of myself in the next unit. We're going to talk about the mole. So let's change that. Get rid of the moles and just put the atomic mass over here. 74.92 grams. So I do that math. I get that each one of the atoms weighs 1.244 times 10 to the 22nd grams. Really, really small. Endpoint, they're very, very tiny. That's actually why we use that Avogadro's number to count atoms, because the atoms are very, 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 very small. Okay, so that's the end of section 2.3. Hopefully that wasn't too long. Gives you a little bit of insight as to how to use the periodic table and how to do some of the quantification of the components. Next time, we're going to do sections 4 and 5. You can start the homework for Chapter 2. Chapter 2 has, much like Chapter 1, has two parts. Has the optional OWL and has the graded OWL. The optional OWL, much like the last one, is in a mastery format. Try it, use it as a good foundation. The graded OWL is going to require you to get points associated with each of the types of problems. And a warning, the unit exam for Chapter 2 is right around the corner. At the end of Chapter 2, which will take another few days, we will get to Chapter 2's unit exam, your first chance to take a real test in Chem 2. So anyway, until next time, I'll see you in class. Take care, be healthy, be happy, be safe. Toodles.